All right. Oh, that's too much. How is it now? Is that okay? Yes. Okay, so this is a quick summary of where we left off last time. So this is a standard way to process continuous time signals. You first convert them to discrete time signals and then process them on your computer and then go back to continuous time with an interpolation. All right? So the question was, can we, although the block in the middle as seen from the continuous time input to the continuous time output is not LTI, it is L but not TI, can we still have a frequency response representation of this? And the answer was yes, if our sampling at the input does not cause aliasing, which requires, of course, from the sampling theorem that first, the signal X is band limited, and the sampling frequency is at least twice as much, or strictly bigger than twice as much as the largest frequency in the signal, right? So under those conditions that guarantee no aliasing, then we can, in fact, take the LTI system, the discrete time system, look at its frequency response, substitute for big omega, which is in units of radians, substitute little omega times t, that just does a correction between the two types of frequencies we talked about, and that will serve as an effective frequency response of the continuous time block. I mean, of the whole orange block that viewed as a continuous time system. Does that make sense? So even though this block is not LTI, we get away with it, and we can still represent it with a frequency response. Okay, clear? The message is clear? Okay, so now let's talk about some examples of this. So let me first ask you the following. So suppose I want to take the derivative of x. I would like y of t to be, ideally, d by dt x of t. But you want to do all of this with a digital computer. So what would you do? How would you design the discrete time LTI system in the middle? There is not one answer to this question, but what are some of the things that may come to mind? Yeah, I mean, you have a discrete time system in the middle. So you're restricted by this scheme, right? You can't just take derivatives. You have to sample first, do something to the samples, interpolate, and you want the result to look sort of like the derivative, at least to approximate the derivative. What would you do? So let's just think together. I'm not hearing too many ideas. So we have this signal, right? X of t. This is our x of t, right? And then we have these samples. Let's say they are like this. So on and so forth. Right? So at this point, I guess this is not, well, okay, that's fine. So let's say at this very point, I want to get an approximate expression for the derivative of x, but all I have are the other data points, not the whole of x. And these things are, all the samples are t apart, remember. Okay, still no volunteers. Okay, let me further restrict your choices. Let's say I tell you that to approximate the derivative at this point, I only allow you to use these two samples, x of n t. So this is x of n t, and this is x of n t plus t, right? What would you do? Look at the difference. Divide by t, right? That's numerical differentiation of the cheapest kind, right? I mean, it's the simplest numerical differentiation you can do. So you can say that dx dt at time equal to nt is approximated by x of nt plus t minus x of nt divided by t. Do you agree to this? Okay, there are much better numerical differentiation methods that use more than just two samples to do this, right? For example, you could go backwards and then also take that into account and get a better approximation. But let's just stick to the simplest and dirtiest derivative, okay? So that would be this, right? So then what's the suggestion? What is the discrete time LTI system doing? Can you give me a formula for yd here in terms of xd in order to realize this numerical scheme? Yes? Wait, where's the deltas coming from? So the question is, so this is xd, when we took samples, this is xd of n, right? This is xd n plus 1, right? So we decided that our approximation of the derivative will be of this type, right? So I'm just asking for a formula for yd in terms of xd. Which is already here. So you have to recognize this guy here, this one, as xd n plus 1, right? And subtract from that xt of n and divide by t. Do we agree? I take samples of x, and if I design the LTI, discrete time LTI system to be this operation, and then interpolate again between the resulting samples, I should get some approximation to the derivative. Does that make sense? Yes? Everybody looks a little suspicious of this. Okay, so that's how you approximate the derivative. So what we want to do now is let's examine what this discrete time LTI system that I just boxed now, with that in mind, what kind of frequency response I get for this orange block. Really, when I see it as a frequency response of x of t in continuous time, what is it? What does it look like? All right? Is the question clear? The answer will become clear if the question is clear. Huh? The question is this. So I want to know the effective frequency response of this thing if I choose my discrete time LTI system to do this thing that I boxed. Okay? All right? We already have the formula. We have everything for it, right? What do I need? So I need to find this expression when the discrete time LTI system is doing this. It's a difference equation, right? And I want to know what frequency response I get, right? So if my LTI system, discrete time LTI system, is defined by this difference equation, yd of n equals xd of n plus 1 minus xd of n by t, right? What is the frequency response? Or if you want, you can start with the impulse response of this. We did this, right? So if I give you a difference equation in discrete time or a differential equation in continuous time, I can ask you, what is the frequency response of this system, right? We saw multiple ways of doing this. One of them goes through the impulse response. You can first look at the impulse response and take the Fourier transform. That's the frequency response, right? Or another way we saw was to just substitute yd to be h times xt in frequency domain and derive it from there. But let's go with the impulse response route. So what is the impulse response of this? When xt is the delta, is that what you were saying? Maybe you are going one step ahead, several steps ahead. Okay, so the impulse response would be what? hd of n equals well, I mean, what do I substitute for input when I look at the impulse response? I put delta, so delta of n plus 1 minus delta of n by t. So it looks very simple, actually. So at n equal to 0, I have negative 1 over t. At n equal to 1, I have positive 1 over t. Otherwise, I have 0. So that's my impulse response, right? It's a very short-lived impulse response because we only took 2 sample points to do the numerical differentiation, right? What did I do? Oh, sorry. Yes, you're right. So let's fix it. Easy fix, turns out. So this is 0, this is negative 1, all right? No, wait, this is, so it has to see the future, right? So, oh, I see, okay. Okay, I won't get away so easily after all, okay. Okay, we still have something on the negative side, right? We anticipate delta, so we start with 1 over t, right? Is that what you were saying? So this is negative 1, and at time equal to 1, well, good, you're at least following. And I'm not. Okay, so negative 1 over t. Is that okay? What am I doing? Okay. I have a 1 over t at negative 1, no? Negative 1 over t should be at 0, you're saying. Ah, okay. And it is. Oh, this is it. Okay, sorry. I didn't sleep much last night, okay? So, 0. Are we happy now? Yes? Okay, thank you. At least you're awake, if I'm not. Okay, so now let's look at the frequency response. Frequency response is, of course, the Fourier transform of DTFT of the impulse response, right? So what is the Fourier transform of delta of n? 1. Delta of n plus 1 e to the j omega and therefore we have hd of e to the j. Oh, I will use the big omega because soon we're going to have to deal with the little omega, which is for continuous time, right? So this is then 1 over t e to the j omega minus 1. All right? It is possible. Is that right? Somehow I'm skeptical. Delta of n plus 1 is shifted to the left. So shouldn't, yeah, that's e to the j omega. Oh, now I know what's going on, guys. Okay. So in my notes, doesn't even matter, but in my notes, I tried to make it causal. As it is, it's not causal, okay? In the notes, I was looking at the current value and the previous value. Whereas what I did here is I'm looking at the current value and next value. Doesn't even matter. We'll get, other than the little phase that this introduces, we'll get the same magnitude for HT anyway. So let me stick to this. The notes will do it slightly differently. Okay, so that's correct. How do you make this look like the sine or cosine? Remember our trick? You factor out e to the j omega by 2, and what is left is e to the j omega by 2, and then I have negative omega by 2, right? And then this looks like 2j times sine omega by 2, right? So the reason for doing this is that this term here, it only gives you a little phase. The magnitude of that is 1. Similarly, j only gives you a phase. So what you're really left with is the sign in terms of magnitude, right? So if I were to sketch this as a function of omega, that is going to be sine, and it will start at 0. It will be 0 at 0, start with slope 2 by t, and then it will reach 2 by t. So that's how the magnitude would look. So at what point do I hit 0? When omega is 2 pi, I'm looking at sine pi. That's right, so 2 pi. All right? So that's actually all I need, right? Because this is discrete time. It's enough to look at the Fourier transform from 0 to 2 pi. Okay? And of course, if I want to look further, it will be simply copies of that. So what I'm drawing here is, so 4 pi, etc., negative 2 pi. So this is the magnitude plot, HD e to the j omega. All right? So, and the peak value is 2 by t. All right? So can you then tell me what is the effective frequency response? To get the effective frequency response, we replaced big omega with little omega times t, right? So we substitute little omega times t. Therefore, we have to divide this by t, right? So that means, it will have the same exact shape, except that we're going to have to correct for the frequencies. Where I see 2 pi is now going to be 2 pi by t, right? Which is the sampling frequency. So this point corresponds to omega s, and this point corresponds to negative omega s. Can you see the bottom? Yes, you can. Okay, good. Right, so it looks the same. So this is what I get when I substitute little omega, big omega by t. All right? So our expression, though, this expression is valid for inputs whose bandwidth stops where? Omega s over 2. It makes no sense if the input somehow exceeds that, right? If the input spectrum exceeds omega s over 2. So therefore, when we write these effective frequency responses, we erase anything that comes after omega s over 2, because inputs that exceed that frequency are not allowed. That expression is not true for them, period, right? So our effective frequency response for the scheme that we discussed is going to give us this expression here. So this is our HF effective of omega, the magnitude of that. All right? Yes? Because 2 pi by t is omega s by definition. And we map big omega to little omega by dividing by t. Okay? All right? So that's the effective frequency response of our method. What is our method? We first sample, apply this numerical differentiation method, and then interpolate and this whole thing combined into one box, if I don't care what's inside the box, what I see from outside is an effective frequency response that looks like this. Is that satisfactory in the sense that if I were actually able to do a pure derivative in continuous time, right? What would have been the frequency response of that? So suppose I can really, without having to worry about the, the hardware to do this, somehow I can just do d by dt as a continuous time LTI system. So this is the ideal case, right? Ideal. How do I take the derivative, right? So what would be the frequency response of this? J omega, great. Why is that? It follows from the differentiation property, right? So when you take the derivative of a signal, what happens in the frequency domain is you just multiply it by j omega, right? Therefore, this block has frequency response j omega, right? So if I plot the ideal frequency response of a differentiator, it's going to go like this, linearly. Omega, so this is the magnitude of h of omega, right? And then like that, right? And it knows no bound, of course. It applies to all frequencies, right? This is the ideal case. What we have is something we can actually implement right away with an analog to digital and digital to analog converter and the CPU. That's all you need, right? How does it compare to this? In other words, how does this plot compare to this plot? So let's try to superimpose them. So the peak value that we reached eventually was 2 over t, right? And the frequency where we stopped here was half of omega s. Remember, omega s is 2 pi by t, right? Half of that is pi over t, right? Is that right? Yes? No? Oh, wait, what's going on? Wait. Oh, no, it's okay. All right. No, false alarm. Okay. And then, so what we have for the effective one is we actually stop at pi over t, negative pi over t, right? So our effective frequency response, just copied from the last page, is going to look like this. Okay? And it will stop here. Why? Because we don't apply any inputs whose bandwidth exceeds that. Okay? So this is H effective of omega. Now, I have shown you something here that I didn't prove, but it should be semi-obvious. So the slopes at omega equal to 0 actually match. The slope of this guy here is 1. You agree with that? Because it's just omega, right? What about the slope of this? I have sine omega by 2. So the slope at omega equal to 0 should be 1 over 2. So that cancels with this 2. Right? Wait, what happened to the... shoot. Okay. Wait. Well, how do we correct for t, though? 2 by t. Oh, here's what happened. Okay. So the expression is this, yes. Let me just write the expression and then we'll be able to remember. So H effective of omega is 2 by t sine omega by 2. Is that right? But omega, remember, is little omega by omega times t, right? By 2. Okay, now the t's will cancel, right? So can you tell me the derivative of this? And there are some j's, of course, e to the j something. I'm sure you're right, but omega over 2 and j, okay. Over 2j. Okay, let me just actually erase this. So let's look at this, and let's look at the derivative as omega approaches from the positive side, because by taking the absolute value, we created a kink here, right? So the derivative is actually not defined, but it is defined if I look at it from the left or right, correct? So what's the value? So you'll get t over 2 from the sign and 2 over t as a factor, so they cancel, right? So it is going to be 1. So the slopes here actually match, right? What happens is that in our discrete time method, we're going to sort of saturate here, level, whereas the other keeps going. And also we stop at frequency pi over t, because any input frequency beyond that is not allowed. Okay? So now looking at this, would you be more or less satisfied with what we've done? Ideal is the blue, orange is what we got. Is that cool? Are you happy? You know, for low frequencies, right? For systems that don't change too fast, for systems whose frequencies are limited to this range, that's pretty good, because the slopes match, right? You're pretty close to the desired frequency response, right? Okay. Not a very responsive crowd today, but any questions? No? Yes. H effective, you're right. Which also is not defined, but you know, from both sides, there is a discontinuity, I guess, at 0. That's all. What we accomplished with this demonstration is that we kind of connected with intuition. Your intuition would tell you that if you apply a numerical differentiation to the samples, you should get something like a derivative, right? So that was the idea here. So we just wanted to see. So our intuition said if we do this numerical method, yd of n, you know, compared to the next sample, divide by t, that should give us something like the derivative when we interpolate back. Okay? So we just built on this intuition and compared the frequency responses of the ideal differentiator in continuous time and this numerical method that works on the samples, right? So what you can accomplish with sampling and CPU and interpolation versus what you would have accomplished if you were able to directly take the derivative. We compared those two. Speak up, please. How are what related? The two frequency responses? So for low frequencies, they look alike. Because if you look at the magnitudes, you know, the slopes match. So for a small frequency range, the two will be very close, right? And presumably you will apply this to signals that are band limited and that don't change too frequently. And therefore, you'll get close answers. Okay? All right, let's do another example. So this time, I'm going to go back to the same thing we have here. So whereas in this example, I wanted to take the derivative of the continuous time signal, in the next example, I'm going to want to do something different. I will want to delay the input signal. Right? So we want to accomplish the following. I would like to build this discrete time algorithm. So remember, the reason I like this discrete time LTI system in the middle is it's one or two lines of code, right, depending on how complicated an operation we're doing, right? So that happens in the CPU, and then you sample, use your computer, and go back. So using this scheme, if I want to have this whole block, the orange block, do the following. Just take the input signal, delay it by delta. All right? That's what I want to accomplish, but again, I'm restricted by the constraints of this scheme. I have to use a sampler, and I have to use a CPU. I'm not allowed to just, manipulate the analog signal, delay it by delta, and speed it up. I can't do, right? But I want to come close to that by choosing an appropriate discrete time operation in the middle. Any suggestions as to what we might do? Delta is a known value, but we want to keep this discussion quite general. I gave you delta, and I said, I want you to make this happen. Write some code. So I gave you the following. I gave you the sampler. I gave you A to D to A blocks. And I gave you the computer in the middle. And I'm telling you I would like to delay the input signal by delta. Write some code for the discrete time LTI system to make that happen. How would you process the input xd of n, the samples, to get that? Yes? Direct delta at the capital delta. Okay, but this has to be discrete time, remember? So you're close, but when I say big delta here, that's, say, in seconds. Right? Whereas you're going to tell me what to do in discrete time with the samples. Yes? Mm-hmm. Okay. You're getting very close, okay. So let me ask you this then. Suppose delta happens to be the sampling period. I'm simplifying the question significantly, right? So let's say, to simplify, delta equals t. I want to delay it by one sampling period. What would the discrete time LTI system do to make this happen? Delay by one, right? Delaying by one in discrete time means I've delayed by one sampling period, and I'm done, right? Does everybody see that? So that means the discrete time LTI system would have to have an impulse response that looks like, actually before the impulse response, basically yd of n will have to be xd of n minus 1. Because the clock ticks here every t seconds, right? Does that make sense? What if delta is, I don't know, any integer multiple of t? Some number m times t, where m is an integer. What would you do then? Then you would delay it by m units, right? M instants. Do you have a question or answer, or just thinking? Uh-huh. No, your process. Oh, well, you're not. What do you mean process point by point? I mean, you may have to have some memory, obviously. Like in this case, you have to store it for m units of time. So you store it and then spit it out, right? But you're dealing with digital equipment. That's the core idea here. So you have memory registers. You can store things and spit them out, but you have to work with digital stuff, right? Okay, so for delta equal to t, the impulse response of the discrete time system would have been just an impulse at 1. That would be hd of n. Or to generalize, if delta is m times t, the impulse would come at time equal to m, right? So that's hd of n, right? And then we'll be done. There's not much to talk about here, right? The interesting question is the following. What if delta is not, what if delta by t, or t by delta, delta by t, is not an integer? What would we do in that case? So I want to delay my signal for half of a sampling period. How do I do that? Do you have an answer? Okay, what's your guess? Uh-huh. But I'm receiving these continuous time things, and I'm taking samples. So I can only work with those samples. Okay? So you're saying do some kind of FFT, and then multiply it with the phase, do inverse FFT, something like that? Yeah, you could do that. That's going to be quite a bit of computation, but yes. Yeah. No, you're not allowed to do that. So this is just sort of a fun exercise. How would we do it? All right? So, well, then we have to think about what we want to accomplish, right? So what is the ideal frequency response? So when I said I want y of t to be delayed by t, what is the h of omega that I'm shooting for, ideally? E to the minus j omega delta, right? Right? That's what delay by delta means, right? So that means I'm trying to accomplish this, right? But with a discrete time LTI system. So that means I could try and match my hd of e to the j omega to this. So I want to make this the effective, right? So how do I make this the effective? So how should I select hd so that h omega is the effective frequency response? Frequency response if hd is selected as how? How do we match those things? We just substitute. We just do a correction for the frequency. Where is the expression? Here. Big omega is little omega times t. So that other than this correction, they have to match, right? So what do I want hd to be then? H of omega, the desired one. When I replace little omega by big omega by t, that's how I go between the two, right? Little omega is big omega by t, big omega is little omega by t times t. So that means what I would like to get is e to the negative j delta by t omega. All right? So that gives me a clue. So whereas when delta by t is an integer, our intuition worked perfectly. We could have an impulse response like this. When we have fractional delays that are fractions of a sampling period, then it's better to go with what we want in the frequency domain and ask ourselves, what is the impulse response that gives me this? Does that make sense? So then the question will become, what is ht of n if this is ht of e to the j omega I want, right? So what is the inverse Fourier transform of this? And that will give me ht of n. All right? That's the question. If delta is equal to 0, what is the inverse Fourier transform? What is the... It's the delta, right? Because this is 1, right? This is equal to 1. If delta is t, then I'm talking about e to the negative j omega. What is the inverse Fourier of that? Which matches what we already had, right? If delta by t is m, an integer, the inverse Fourier is a delta centered at m, which is this, right? So, we recovered everything we already had, but we can go beyond the integer cases. All right? So, turns out, if you do the math, which is not hard, but, we don't need to go back to Fourier transforms at this point. If you do the math, you're going to get this ht of n. ht of n is going to be sinc n minus delta by t. Right? So we all know what a sinc looks like. So it's that sinc, except that it's shifted by delta over t. Right? So that's ht of n. Now, also keep in mind that n is not a continuous variable, and n consists of integers, 0, 1, 2, etc. Right? So therefore, if delta is t, let's draw this. Let's first draw it as if it's a continuous function of it's a function of continuous variable n, right? It's going to be centered at delta over t, which is 1, and it's going to pass through 0. I'm going to try to do a careful drawing here. How am I doing? Good. All right, does that look like a sinc? All right. I actually did a pretty good job, so I'm going to copy this so I don't lose it. So copy, paste, and paste again. Okay. Now let's work on the case delta equal to t. Of course, n is not a continuous variable, so we only talk about n equal to 0, 1, etc. Right? At 0, I have this value. At 1, I have this value, which is 1. And then I have this, right? So I've actually recovered what we had, right? If delta is equal to t, we wanted the delta, Dirac delta at n equal to 1. That's exactly what comes out of this, right? So it recovers what we had. If delta is, say, 2t, then, then this guy is going to go here, so that this becomes 2. This becomes 2, this becomes 1, so it's going to have to cross at 0, right? Okay. So that's what sinc n minus 2 then looks like, right? So, and again, I'm looking at integer values of n, so I have this, and zeros. Okay? So this is a delta centered at 2. Okay? So far, nothing interesting. These are all reproducing what we already know we should do when the desired delay is an integer multiple of the sampling period. Here's the interesting question. Delta is, let's say, half of t. How do I delay the signals which I sampled by half a sample period? Right? What does it look like then? So now I'm talking about sinc of n minus 1/2. So the peak of the sinc happens not at 1, not at 0, it happens at 1 over 2. Right? So I'm going to have to move this guy to 0. So this point is really negative 1 over 2. So now look at the zero crossings, right? It happens at halves. 0.5, 1.5, 2.5, 3.5, etc., right? And then 0 is here in the middle. So something funny happens now, right? So now when I look at this signal sequence, HD of n, right? That corresponds to this octopus, the orange thing at in the background, sampled at 0, 1, because it's centered at 1 over 2, those two values will match. Does that make sense? Because it's symmetric, right? And then at 2, where are you going to get this? At 3, you're going to get this. At 4, you're going to get something here. And this will continue like that. All right? So unlike HD of n for the first two cases where delta was an integer multiple of t, now the HD of n is much more complicated, right? Because we're looking at values of the sink at non-integer argument values, right? So if I want to delay, so the conclusion is this. If I want to delay an incoming signal by half of the sampling period, this is the amount, this is the impulse response that your discrete time system would have to implement. Okay? So why does this work? Why does it really delay by half a period? Right? Well, let's see what's going on here. So what is YD is going to look like if I choose my HD to be this, right? What is the connection between YD, HD, and XD? It's convolution. XD of n, right? So I know XD of n, they are the samples of the incoming signal. HD we just calculated, right? So if I write the expression for convolution, I can just say this is a sum over k. K is going to be our dummy now. XD of k times HD of n minus k. The good old definition of convolution, right? And I know what my HD of n is. It's given here. So I'm going to shift that by k. And we write it. So we have k, XD of k, sinc n minus delta by t minus k. All right? And this XD, remember, this guy here, are just samples of x. These are x of kt. Right? All right, so last time we talked about reconstructing a signal from its samples, right? Do you remember the expression for the reconstructed signal when we do sinc interpolation? You take each sample, multiply it with a sinc centered at that sample, right? Sinc of t minus kt by t. And you sum those over all the samples, and that's the nice and smooth interpolation between the sampled values, right? So how does this expression here compare to the reconstructed signal? What's the connection? Does it look like it? Two things are happening, right? First, in place of little t, right, we have written little n times the sampling period. That's one difference, right? So I want an expression in terms of XR here, okay? I want you to tell me that this is equal to, this whole thing, YD of n, is equal to XR of something when I'm looking at the samples. First, there's a shift, right? By how much? By delta. So if I shift XR by delta and substitute n times t. So if I shift my XR by delta and then look at the samples, do you agree that you recover the same expression? Just comparing this to this. Yes? Okay. So take that t, subtract delta, you have delta by t, and put little t equals n times capital T, and you'll get the same expression. All right? So what I just wrote gives us a lot of insight about what's happening here. So although this looks very complicated, this impulse response for a fractional delay, it actually, what it's trying to do is it's reconstructing what the signal would have been in the midpoints. This is the point that I really would have liked to know, right? These are the values that I would have liked to know. So it's trying to reconstruct those, okay, using the sinc interpolation. So at the end of the day, you know, YD of n matches a reconstructed x shifted by delta. Therefore, when I take these samples and pass it through the reconstruction filter, it's going to give me XR of t minus delta, right? So look at this again. It may take a little time to sink in, but it's quite amazing how you actually accomplish, how you manage to delay a signal by a fraction of the sampling period using only the samples. And the essence of this is that you actually use interpolation of the samples you don't know, right? And then use those interpolated values as the fractionally delayed signal, right? So hopefully this gives you some conviction that this scheme we proposed here can do more than what's obvious, right? So obvious things were how do I take the derivative, or how do I delay by one sampling period. Less obvious is how do I delay by half a sampling period, and still you can work through the machinery and find an appropriate LTI system that should go in the middle. All right, so let's take a short break, and then we continue after. e to the negative j whatever, and then do an inverse of it. You can do that too.
You just do that because it's easier to do like the
Well, I'm also trying to give you the intuition about the frequency responses and things like that. Right? Yes.
Is there a linear algebra way to think about like the sync function?
Linear algebra way to think about the sync function. More specifically,
Like the way that I learned Fourier series in like Math 54 was it's all projections with your basis functions being like exponentials with different frequencies.
oh, okay.
So considering like it seems like the sync function is doing something similar, where it's like taking like a discrete like sequence of points and like it's like you're projecting it somehow or something. It's like
Oh.
so I was just wondering.
Oh, I see. That's what you mean. Okay.
Yeah.
I see. Okay, you could say linear algebra. Yes. Okay. Yes. So the sinks are essentially a basis. I mean, that's one way to think about it. The shifted sinks are a basis for band-limited signals.
Oh, okay. And so that's what allows us to keep circling.
Yeah.
Okay.
That's basically it. Yeah.
Okay. And then I have one other question.
Uh-huh.
This one I don't know much about, but so I'm trying to decide classes to take the next semester, and one of the things that looked really interesting that I don't know anything about is like Lie groups or like Lie groups. I don't know.
Lie. Uh-huh.
And like I looked up like the syllabus, and it's like one of the first examples is like the unit circle.
Hmm?
And since like all this stuff is related to unit circle, I was just wondering if like it's use if like understanding stuff like that is would be helpful for understanding.
Yeah, there are Fourier transforms on groups, so it doesn't even have to be So we do the unit circle essentially, but on other groups you can define analogs of these transforms. Yeah, it's good stuff. Lie groups have a lot of uses.
Any particular application that relies upon
Robotics.
Requires Lie group?
Yeah, a lot of it. Or anything like controlling the attitude of a satellite. So it's basically evolves on a Lie group. So because it's not like, it's like a circle. So you can rotate. Rotation matrices basically form a group.
Okay.
So therefore you need an appropriate representation of that. The rotation matrix in 3D is like a 3x3 thing, right?
Yeah.
But it has symmetry. It has 6 independent values, but you can actually parameterize it in different ways. So there are parameterizations that use 3 parameters. There are parameterizations that use 3 and one more that can be +1, -1. It's called the quaternion.
Yeah.
It's really cool stuff. I mean,
Do you know if the class on Lie groups here is good, or if like I should just go and take like 106A, like E106A, or like?
I don't think 106A will probably be a little much more applied. Are you a math major?
Yeah. Sorry.
Yeah, go for Lie groups. Yeah.
Okay.
And stop by next semester. I'll give you some references to read to make the connection to attitudes and stuff like that.
Okay. Cool.
All right? Okay. So I want to close today's lecture with a discussion of sampling discrete time signals. Okay? If I can sample continuous time signals, why can't I sample discrete time signals? That's not fair, right? So here's the idea in a picture, very simple. Let's say I want to sample with a sampling period of 2. Now we're in discrete time. Sampling period can only be an integer, right? So I have x of n, and I want to sample it with a sampling period of 2. Here's one way to represent this. So you just eliminate the odd-valued n's, okay? And what remains is the sampled signal. Okay, is that obvious? So if I give you a signal, discrete time sequence, and if I say sample this with period 2, does it make sense that you keep alternate values and drop the ones in the middle? That's the idea. If I give you n equal to 3, keep 1, drop 2, keep 1, drop 2, etc. Right? So to be sort of consistent with the way we did this impulse train sampling in continuous time. We introduce impulse train sampling in discrete time as well. First, we introduce an impulse train P, which is a sequence of impulses that are spaced capital N units apart. So P is going to look like this. An impulse at 0, and then zeros, an impulse at 1, and so on and so forth. So this is our impulse train, P of n, right? If I multiply x and p, what p will do is it will kill these intermediate things, right? So if I'm doing sampling with period 3, it will keep 1, get rid of the other 2, keep 1, get rid of the other 2. Because you're multiplying, you get 0, right? That's essentially what happens. So this is illustrating sampling with a period of 2. So these guys will be eliminated, right? And the way it happens is you multiply it with this impulse train, which only happens at even n's. It's 0 at odd valued n's. So when you multiply, the odd values n's drop out. They become 0. Okay? Any questions? Is that how you would have done sampling on a discrete time signal if I asked you to? No? Maybe you would have done it a little differently, possibly. So the way I define it, xp of n is a sampling of the discrete time signal x of n, right? If I just didn't show you this plot and asked you to do it, how would you have done it? Same way, or would you do it something different? Yes? Yeah, so why would I put those zeros in the middle, right? That's another way to do it. So that's perfect. That's perfectly fine. In fact, maybe a little more intuitive. The only reason we are doing this by putting zeros in the middle is because we want to maintain the consistency with the impulse train in continuous time. Okay? So this is sort of an intermediate object. There is absolutely no reason to store zeros in memory, allocate memory registers to store zeros, right? You would really compress this, right? And you would only keep these values. And you wouldn't worry about the zeros, right? That's really called, when you ignore those zeros in the middle, that's called downsampling. You keep every nth sample, drop everything else in the middle, okay? When we keep the zeros in the middle, only for mathematical convenience, no other reason, not that we would want to store zeros, that's called impulse train sampling. Okay, so that's the difference between the two. Downsampled signal doesn't keep those zeros in the middle. Impulse train sampling keeps the zeros in the middle. Okay, only difference is that. Okay, but for now, we stick to impulse train sampling, so we will have to live with those zeros in the middle. All right? So now let me ask you this question. Actually, we can ask the same types of questions we asked for the continuous time case. So if I sampled my discrete time signal, kept only the nth other sample, could I possibly reconstruct the values I threw away, that I crossed out in this picture, from the ones that I kept? And that's the essence of the Shannon-Nyquist theorem, although we're asking the same question now in discrete time. Okay? What do you think the answer would be? Yes, if, blah, 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 right? Two things. If there are two ifs, right? First if is that you want your signal to be band limited. And then next you want your sampling to be fast enough relative to the bandwidth. And we'll make that a little more precise, which will look just like the Nyquist-Shannon theorem, no difference really. It will just have to be adapted to this situation, to the discrete time case. Okay, but then, so the question here is we require reconstruction and recover the same signals, same values we dropped, right? So what kind of reconstruction do we do for band-limited signals? Sinc interpolation, right? So it's going to look actually very similar to the sinc interpolation we did in continuous time. To each of these non-zero samples we have, the ones we kept, The others we set to 0, right? The ones that we kept, they are going to multiply with a sinc that will fill in the space in between. And we'll add them up, and it will smoothly interpolate them. And more precisely, this is what the interpolation will look like. It really is very similar to what we did in continuous time. In continuous time, we had xr of t, x of nt times sinc t minus nt by capital T, sum over n. That was continuous time. So this is the discrete time version of that. Same idea. All right? So now look at this expression 3. It has a bunch of these sinc n over n terms in it, right? And each of these is recentered at an integer multiple of n, k times n, right? So without that shifting, what does sinc little n by big N look like? Normally, sinc crosses 0 at integer values, right? When n is an integer, it will cross 0. When we do little n by big N, it will cross 0 when little n becomes capital N, or 2 times capital N, or 3 times capital N. And that's exactly what you see at the picture below, right? So this is sinc n over big N, and the 0 crossings occur at integer multiples of big N. So therefore, can you picture in your mind what's happening in equation 3? To each sample, you have one like this, right? Centered at where that sample is, right? And then you add those up. If you twist your eyes, can you see what's going to happen? So I have only samples. Let's say I'm keeping every 10th sample. N is 10, right? And to each one, I'm attaching a sinc that crosses 0 at 10 and 20 and 30, right? And they are shifted by 10, 20, etc. And I'm adding those up. All right? Can you see it in your mind? Okay. It's better to force you to think about it before actually showing you the picture. Okay, so here's an example. So we have a signal that's sampled with n equal to 10. So we threw away 9 samples in the middle, kept every 10th, right? So it looks like this. When I'm doing the reconstruction, I'm attaching to the first sample at time equal to 0 a sinc n over 10, right? Which looks like the second plot from the top. To the sample at n equal to 10, I attach a sinc centered at 10, and that's the plot, the third plot from the top. And for the sample at 20, I have another sinc centered at 20, and that's the penultimate plot. And if I add them up, that's the reconstructed signal. Right? It's nice and smooth because sinc functions are smooth. Make sense? Okay, so that's the idea in the sinc interpolation. That really is a picture of this equation here that I circled. Okay? Any questions? Is that all clear? Okay? So the idea is, I had a signal, x of n. I kept only the 10th values. Okay, so now it looks like this. Does that interpolation at the bottom recover the signal that x was in the first place? Right? The answer will, of course, depend what was dropped, right? If that signal was crazy, if x of n was crazy, right? If it had values that jump up and down, like, you know, if the ones we dropped were really jumpy like this, it will, of course, not match this reconstructed value, right? But if x in the first place was nice and smooth and band limited means really nice and smooth, right? Can't vary too much. If x in the first place was band limited, then it's reasonable to expect that this xr, the reconstructed thing, will actually capture what the signal was in the first place, right? So the rest of this story is really identical to continuous time. I'm only going to walk through it just to make sure that you understand the general story. So to answer the question of whether or not we are reconstructing X, we can view the reconstructed signal XR as the output of an LTI system, right? So the response of the LTI system to a single delta, look at this for example, is going to be a single sync, right? So if I give this delta, right, it's giving me this one. So that's the impulse response of the LTI system, right? Which is sync little n by capital N. So the reconstruction, the interpolation, the sync interpolation we're doing here is really the output of an LTI system with this HR to this input, right? So apply this HR to this input, XP, and it will give you this output. You agree with that? Okay. And if I ask you what this LTI system is, what kind of function it performs, yes, it does sync interpolation, but what is it? If you looked at it in the frequency domain, it's a low-pass filter. In fact, it's an ideal low-pass filter. Sync, remember? Syncs are ideal low-pass filters. The only question is, what is the cutoff frequency of that? And you can answer that by taking the Fourier transform, DTFT of this HR. It's going to look like this. Okay? Cutoff is pi over n. Of course, this is DTFT, right? So it's going to be periodic with 2 pi and all that. You know this. And then the amplitude is n. Okay? All right. So basically, we've low-pass filtered. It's kind of interesting, right? So you take this XP, you low-pass filter it with cutoff frequency pi over n, and you get this reconstruct interpolated signal. Sync interpolation is really low-pass filtering. Nothing more. That's it. Okay? All right. So then, let's see under what conditions would we really be recovering at the output of this low-pass filter the actual signal X, right? Clearly, because XR, the reconstructed signal, is the output of this filter, its bandwidth can't exceed pi over n, right? Because anything else is killed by the low-pass filter, right? So XR is band limited by pi over n. If the signal X did not obey the same band limit, is there any chance that the reconstructed signal can recover X? The way I asked it, the answer is obvious, right? You should say no, right? Because X doesn't have the same band limit, but by reconstruction, we have a low-pass filtered signal with this cutoff, right? Therefore, the reconstructed signal can't exceed this bandwidth, right? So it's clear that this Shannon-Nyquist criterion, the bandwidth limit, is a necessary condition. Otherwise, there's no way these two things will match, right? You can't recover a signal with a lower bandwidth signal, right? So that part is clear. The rest is, do we exactly get X? And the answer is yes, because this is an ideal low-pass filter. The way it works is we first notice that XR, I hate that now. XR is HR times XP, right? The Fourier transforms. HR we know. The only question to be able to compare XR to, the only way to compare XR to X is to first link XP to X, right? What is the connection of XP to the Fourier transform of X? And you did this in the lecture 2 lectures ago, right? Last Thursday for the continuous time case. So something very similar happens. So I will first tell you what it is, and then we can go back and discuss where that came from. But very similar. Remember what happened in continuous time when you were doing impulse train sampling? You were just getting copies of the shifted copies of the spectrum, right? If this was your x of omega, you were getting the same thing, only scaled by 1 over t, and they were omega s apart, where omega s is 2 pi over t. Remember that? That was xp of omega. You remember this, right? So what I'm claiming here is something very similar in discrete time. So this is the Fourier transform of the impulse train sample discrete time signal. And it again consists of shifted copies of the original DTFT. It's scaled by 1 over n, just like this was scaled by 1 over t. And the copies are 2 pi over n apart, just like the copies here were 2 pi over t apart, right? Everything is analogous, okay? So so what happens is, we take this XP, it's going to look like this, we low-pass filter it. And the cutoff of the low-pass filter is half of omega s. Okay? And then we ask, have we recovered the original signal? And the answer is depends. If you did not sample fast, the question is, going from x to xp, did x remain intact? Or did it get aliased? Right? To remain intact, you have to make sure that the samples were separated well apart, that there was no overlap. Okay? And that happens if the bandwidth, which is this highest frequency here, omega m, is smaller than omega s over 2. Right? So if you're band limited by omega m, and if you sample more than twice as much, with a frequency more than twice as much, then there will be no overlaps. And therefore, when you restrict yourself to this period of frequencies, it's going to look exactly like x, right? Other than this 1 over t factor or 1 over n factor here, right? And once you low-pass filter it, and remember that 1 over n is corrected for by this, right? Once you low-pass filter it, you get exactly what x was in the first place. And that's how the Shannon-Nyquist theorem works, how it's proven. Okay? So same exact idea. 2 key conditions. One is this, band limited by omega m. Of course, we have to write it appropriately because in discrete time, the spectrum is periodic with 2 pi, right? So I can't just say after omega m, this is always 0. No, it's going to come back at 2 pi again, right? So I account for that with this expression. So I limit myself to negative pi to pi and make my statements there, right? Because otherwise it's periodic. And then I want to obey this bound. The sampling frequency has to be large enough. And under those, I recover the same thing. So this is the picture, similar to the picture in the continuous time case. This is the DTFT of our signal x. Again, somehow triangle. It doesn't have to be triangle, of course, but band limited by omega m. The impulse train sampled version of that will consist of shifted copies. So this example, this figure here illustrates this for n equal to 2. All right? So they are separated 2 pi over n apart. And then the amplitude is divided by n. Right? So the conditions, the band limit condition and sampling twice as fast, guarantee that from half the sampling frequency, from negative half the sampling frequency to the positive half sampling frequency, you match xp other than this factor, which is corrected for with the filter, and you get the same thing. The reconstructed signal matches the original signal that was sampled in the frequency domain, therefore in the time domain as well. So this leads us to a sampling theorem of sorts, except that it's now for a discrete time signal. Okay, same exact condition. X has to be band limited, and then it has to be sampled at higher than twice the bandwidth, and then you will recover the same signal. Right? Same story told differently in discrete time, but otherwise it's the same exact ideas. All right, questions? Okay. Now, I'm going to skip this because you guys did this for continuous time impulse train. It's even easier in discrete time, so it's written in the notes. You can look at it. So this explains why this expression was correct. Yxp, equation 6. Yxp consists of shifted copies of x, right? Why does impulse train sampling do that to the Fourier transform? Okay, so that's obtained from the convolution property because we obtained xp by multiplying x with the impulse train. That means we convolve their Fourier transforms in the frequency domain. So look at the notes, you'll see why that follows, but the important part is the sampling theorem. All right? No questions? Okay, so when you do digital signal processing, for example, if you take 123, you'll probably talk a lot about upsampling, downsampling, and things of that sort. So I want to connect those terminologies to what we've already seen, right? We only talked about impulse train sampling, which meant we kept only the nth sample and put zeros in the middle. You told me it may have been more natural to not have those zeros, so to compress the sequence. That's exactly what downsampling means. All right? And people use this arrow notation for downsampling, right? So you have a sequence. Downsampling means keep every capital nth and discard the rest. So the picture at the bottom is what that means, right? The values 1 to n minus 1 are gone. You've only kept x of 0, x of n, x of 2n, etc. All right? And the figure at the top contrasts this to the impulse train sampling that we discussed, where we had kept zeros in the middle. All right? So downsampling is the one at the bottom. Okay? So what do you think upsampling means? But to interpolate, first you have to make room for them, right? If I give you a signal, if I say, upsample this. This was the sequence. I want you to upsample this. That means I want you to fill it in interpolated values in the middle, right? But first you have to stretch it so that there's room for those new samples you're going to generate. Okay? So that's the first step. For lack of a better notation, I call this, I put this. Because for downsampling, they use this notation, right? Arrow down, and that means down sample by n. Keep fewer samples. Keep every nth sample. Upsampling, they will use this notation. But to do upsampling, first you have to stretch it and put zeros in the middle. And for that, I use this notation in the notes. That means stretch, like pull it apart, right? I totally made this up, but I kind of like it, actually. So this is the picture. You start with y. First, you make room, stretch, right? And then you do your sinc interpolation. Fill in the values in the middle. And we already discussed that. This is the usual reconstruction, low-pass filtering that we already discussed, right? Make sense? And that is called upsampling. So when you hear these words, upsample, downsample, you should not freak out. It really is the same things we did, right? The only difference is that when we did the impulse train sampling, we put zeros in the middle. And when you upsample, downsample, you don't do that, all right? That's the only difference. Okay? So, and naturally, if I give you a signal and tell you first to downsample it, and then I say, oh, I changed my mind, can you upsample again? But then you already discarded the values in the middle, right? When do you actually not lose any information? When can you actually perfectly recover? All that again goes back to the sampling theorem we discussed, right? If you had kept unnecessarily many samples in the first place, if you had sampled a lot more than the Nyquist frequency, kept many more, then there's a lot of room for you to further downsample and still retain all the information you need to fully reconstruct it, right? Okay? So what might be some applications of upsampling and downsampling? Can you think about it? Okay. Like what? I mean, okay. Yeah. How about upsampling? Higher resolution. I'll give you an example, and I won't have to go too far to give you an example. Here, I'm doing it. Now I'm downsampling. Now I'm upsampling. So you do these things in image processing a lot, right? Because when I'm doing this, I've created a bunch of new pixels that need to be filled in. How am I going to fill them in? I have to do some kind of interpolation. It probably will not be the ideal sync interpolation because that's an infinite impulse response filter, right? You can't really implement it with finitely many things, but it will probably be some kind of approximation to it, right? Speaking of which, sampling can also be done in 2D, 3D, whatever dimensions you want, right? Same ideas apply. I'll just show you a couple of pictures. We don't need to overdo this. So the reason 2D is particularly important is because that happens in image processing. I just showed you examples of upsampling, downsampling. So you need to do these in 2D. So let's imagine we have a continuous signal. I'm not going to say time now because time is usually 1D. But to stick to our notation, I'll just call it T1, T2. Most likely this will be X and Y dimensions of an image, for example. Or you could have 3D where you have time, X, Y, so it's a video. So we've taken samples. Now you have 2 dimensions in which to sample. And therefore you can select different sampling periods in each dimension, right? You can choose T1 in the little t1 direction, and you can choose another capital T2 in the other direction, right? And the impulse train sampling could then be described as the multiplication of X with an impulse train. Now the impulse train is not a 1D thing. It is more like, imagine a function of 2 variables, T1 and T2. So you're going to have needles coming out, T1 apart here, right? But also T2 apart here in this direction. So it's like a grid, right? So imagine like a plank with nails on it, right? I mean, yeah, it's a silly comparison, but it's like that, right? So you have a bunch of impulses coming out. They are separated by T2 in one direction and T1 in the other direction, right? And then my X of T was a continuous surface in the T1, T2 plane, right? So when I multiply them, I will just keep the needles, except they will be amplified or attenuated by the values of my surface at those points. And that's basically what xp of t is. It's a product of x of t and p of t, right? So if I take the Fourier transform, same ideas, just like what we had here, we're going to end up with copies, shifted copies of the DTFT. But now DTFT itself, or CTFT. CTFT itself is a 2-dimensional thing, right? It's a function of omega 1 and omega 2. There are 2 distinct frequencies, 2 independent frequencies. So the CTFT itself is a surface in the omega 1, omega 2 plane, right? Something like this, right? So what we are doing now is we are making shifted copies. We are shifting it both in the omega 2 direction by 2 pi over T2, right? And both in the omega 1 direction with a difference of 2 pi by T1. So, and we add them up. That's basically what this expression at the bottom says, okay? So the copies now happen in both dimensions. And then we interpolate. Actually, the interpolation is at the very bottom. So this is the interpolation we do, right? And then we ask, am I recovering the same thing? It's the same exact story, except that the interpolation is a little more elaborate, of course, because we are multiplying with sinks into the product of two sinks. Oh, this is wrong, of course. This is T. Everything here is T2. When you copy and paste, don't forget to change the indices. Note to self. Okay, I'll have to fix that. So the second one is T2. Every subscript 1 in the second expression is 2, right? 2 here, 2 here, 2 here, 2 here. Okay? So now we discussed 2D stuff some lectures ago, and if I can pull that up. Yeah, here. So this is the product of two sinks. Sink of N1 times sink of N2, right? So basically, when we are doing interpolation, we are attaching one of these at every sample point. And taking another one, putting it, centering it at the other sample point, and we're adding them up. Just like we did interpolation in the 1D case, right? So this is sink interpolation in 2D. All right, so where was I? 214. Okay, so basically that's what this expression says, right? To each sample, to each needle here, sample needle, I attach one of those 2D octopus functions and add them up, and that gives us a reconstruction. Question is, does XR match X, whose samples I took in the first place? And the answer comes from the usual things, right? I'm going to have to make sure that this XP, the Fourier transform, which consists of shifted copies, do not have overlaps. All right? So the copies are shown here. This is a view from the top in this picture, right? They are separated by omega S1, which is 2 pi by T1 in the omega 1 direction, and 2 pi by T2, which is omega S2 in the omega 2 direction, right? So that's why the view from the top looks like that. And the bandwidth is omega M1 in the omega 1 direction and omega M2 in the omega 2 direction. To make sure there is no overlap, I have to make sure that omega M1 is less than half of, make sure those squares don't overlap, right? Half of omega is 1, right? Similarly, omega M2 should be less than omega S2. Then these will be intact. And when I low-pass filter it, with an ideal low-pass filter whose cutoff is half of omega S1 and half of omega S2, I'm going to extract this more darkly shaded component, right? So the low-pass filter will do this. It will have cutoff equal to omega S1 by 2 and cutoff omega S2 by 2 here. And everything else will be eliminated, right? So it will keep this, and that's the same as, under our conditions, that's the same as Rx. Okay? So the reason I'm showing you this is there's really no reason to restrict ourselves to 1D. That's a very narrow world. Okay? And when I do these things, basically things were happening in 2D anyway, right? So we are doing the expansion and the upsampling in 2D, right? Now, this is when T1 and T2 are continuous variables. You can totally extend this to the case where they are discrete, so then you can talk about digital image processing, right? Same ideas. Any questions? I went a little fast because I was not writing anything and going through the notes, but maybe that's a good thing. So I guess what I'm going to do is I'll just leave the floor open to any kind of question, whatever you want to ask. Can be anything. Preferably sampling the past 3 lectures, but if you want to go beyond that, that's also fine. Yes. No. I mean, sync is an idealization. It's not just like ideal low-pass filter, which sync really is, right? So typically, you just truncate this, you taper it, and all that stuff, right? Or people use other kinds of low-pass filters. For example, in image processing, it's very common to use the Gaussian low-pass filters. Remember the Gaussian function? And then you guys calculated the Fourier transform of that, and it was again a Gaussian, slightly scaled, right? So people kind of like that because it looks the same. It's the same bell-shaped curve, whether it's in the original domain or in the frequency domain, right? So yeah, that's actually commonly used in image processing. Photoshop, when you do edge detection and things like that, these are all applications of these LTI operations, really. There is a course, computational photography. Has anybody taken it? No? Really cool course. I don't know if it's still offered. It used to be offered. Oh, I see. But he'll come back. So it really is a great course. I think it makes everything very intuitive because you play with images, you do stuff, and you kind of get a nice feel about how these things work. So all these convolutions and everything, one course is not enough for convolution to fully sink in. I mean, you can do it mechanically, but it takes seeing images. But just keep in mind, when you're playing with Photoshop, you're doing a lot of convolutions, you're doing a lot of filtering, you're doing all kinds of LTI operations. Other questions? Yes. The actual width of what? I'm sorry? Okay. Okay. I'm glad you asked because I think we need to make that very clear. So our perennial picture is this, right? You have x of omega with omega m. We're in continuous time now, right? So this is the CTFT. So are you asking why xp looks this way? You remember there are two differences. First, you have a scaling of t. If it was 1, it will be 1 over t. And then the next copy will come at omega s, which is 2 pi over t. If you believe this picture, we can talk about why this is true. But if you believe this picture, it should be clear why I want twice. Because omega m is here, right? Half of omega s is this, right? Half of omega s is the middle. If omega m goes over that half, they will start overlapping. Okay? So that's the critical part. That's why we need omega s bigger than 2 omega m. And one question last time was, why strictly positive? Well, in this picture, it's not clear in this picture. Why? Because in this picture, we are using triangles that's already 0 at omega m, right? But in our examples, we talked about sinusoidal things that had spikes at omega m. So you really want to space them apart so they don't ever overlap, right? So that's why we have strict. Now, the other question is how do you go from here to here? And the trick there is, first we write xp of t as the product of x of t with an impulse train. This, right? Separated by t. Right? And then the thinking is that this, even though it consists of these impulses, it is a periodic signal, so it should have a Fourier series, right? Turns out when you find the Fourier series of that, the Fourier series coefficients are all equal to 1 over t. it actually follows directly from the formula by which we find AK. Remember, we have to integrate over a period of t. So if I choose that period to include the first copy, we're just integrating the value at t equal to 0. And no matter which harmonic we're looking at, e to the j omega whatever, it's going to be 1, right? And we divide by the period. That's where this 1 over t comes from. So for all k, it's that, right? So signals that are periodic and therefore have Fourier series, you can also talk about the Fourier transforms of those, except that at those discrete frequencies, you're going to have impulses also. Okay, that's why we talked about those distributions, whatnot, because the usual Fourier transform doesn't converge because these are sinusoidal things. You integrate from negative infinity to infinity, it's not going to converge anywhere. But the theory of distributions allows us to define the Fourier transform in this way. So this is P of omega. And these are separated by omega s to omega s, etc., which is 2 pi by t, right? Because it's a product in time, in the frequency domain, it's a convolution. Convolution with a delta does nothing, right? Convolution with a delta at omega s, again, does nothing except that it shifts by omega s, right? And that's exactly why you get this copy. That's a result of convolution with this guy, right? This one here is a result of the convolution with that. So each of these spikes will lead to a copy. And then you don't want those copies to overlap. That's why we ask for this condition. Okay? All right. You look like you want to stare at this a little longer, which is a great idea. Lecture notes are good to look at. And then the homework will come soon as I can come up with one. Could be as early as tonight or tomorrow morning, I don't know when, but you'll have enough time. Whenever it happens, you'll get at least 1 week from there. Okay? All good? How did homework 3 go? Are you done with it? Cool. Okay. So I have 5 more minutes. So if you have homework questions, if you're having a last-ditch effort to do the homework in the remaining 5 hours or whatever it is. No, 10 hours, right? Midnight. Is it midnight? Oh, you have 10 hours. Have you even started?